right, our final test. We're going to lead in with this. So would you agree that the series diverges? So looking at this, if you have 1 and then add on a half forever, hopefully you can tell that that's going to keep getting bigger by a half forever. So that's going to diverge. So I told you earlier to just trust me that the harmonic series diverges. So the harmonic series is this first one. It's the 1 over n. So in that series, you just keep plugging in the different numbers on the bottom. So plug in 1, plug in 2, plug in 3. So this is the harmonic series. So we're going to prove that this diverges by comparing it to another series. So the series we're going to converge it to is this one. So notice we start with 1, then we have 1/2. Then if I combine together 1/4 and 1/4, I get a half. If I combine together all these 1/8, I also get a half. So this pattern is going to continue. It's going to keep equaling a half. So if we do 1 plus a half plus a half plus a half, we just said that that diverges. So if we compare the harmonic series to this series, here the terms match. Here 1/3 is a little bit bigger. But then as we go, notice 1/5, this is going to be bigger than 1/8. 1/6 is bigger than 1/8. 1/7 is bigger than 1/8. So these top terms all are bigger or the same as the terms on the bottom. So because they are larger or the same, terms in number 1 are greater than or equal to their corresponding terms in number 2. And since we know that number 2 diverges, it's adding a half forever, number 1 also has to diverge. So when you have a series that is bigger than a series that you know diverges, it is going to diverge. So we're going to formalize that in the next slide. So seeing that again, I'm comparing these two series, and I know for sure that this one diverges, and I want to use it by comparison to help me prove that this diverges. So what I did was I wrote out the first 5 terms in both of these series, and then I compared them. So to start with, I'm looking at them. When you compare like the terms that are in the first spot, the second spot. So you compare them to their corresponding term. So looking at these, you can notice that like 3/5 is bigger than 1/4. 3/6, that's 1/2, that's bigger than 1/5. So these terms on the top are bigger than the terms that are in the harmonic series, the 1 over n. So because these terms are bigger than terms that we know diverge, this one is also going to diverge. So that's formalized down here. It says series 2 diverges by p series, so we know it's harmonic. Series 1 is always bigger than series 2, so therefore series 1 diverges by the comparison test. So I summarized that in my own words. I said if the terms in the series are bigger than a diverging series, then the series must also diverge. This works a little bit differently for converging. So earlier in our statement, we asked, this was our warm-up in the folder. So we want to prove whether this converges or diverges. So my guess was that it converged. So what I did was I compared it. I know that 1 over n squared converges by p series because the 2 is greater than 1. So we know that this one converges, so we're going to compare these terms to it. So as I went, 1 and 1 matched. Here, 1/2 was bigger. Here, 1/6 is bigger. 1/24 though, now we're getting smaller. So now this one's smaller. Comparing here, this one's smaller. As we keep going, even though originally the top were the smaller ones, as you go and your terms keep getting bigger and bigger, it's clear that 1 over n factorial, those are going to be smaller every time than the terms on top. So because these terms are smaller than a series that we know converges, this series is also going to converge. So we know that this one converges by p series. These terms are smaller than a converging series, so it also has to converge because we know it's smaller than something that converges. So conclusion for that, I said we know series 1 converges by p series. After the third term, series 1's bounds, traps, or dominates series 2. Therefore, series 2 converges by comparison tests. So I don't really like the whole bounds, traps, dominates, so I think about it as it is smaller than a converging series, so it also must converge. So finally, I sum that up. Just in other words, you can prove a series converges by trapping it below, so making it smaller than a converging series. And you can prove a series diverges by trapping it above another diverging series, so making it bigger than a known divergent series. So this can be a little bit tricky. When we're doing this, If they would give you a problem like this and say, prove that it converges or diverges by comparison test. So what I would do is make a logical guess, like I think this probably converges, and then try to trap it below something you know converges. Usually I'll use a p-series test for that. So whenever I compare, I usually will use 1 over n squared or 1 over n, because I know that 1 over n diverges, 1 over n squared converges.